Okay, in this video, we're going to get started with the introduction to computation and programming using Python textbook. In this video, we're going to go through the opening chapter. Getting started. Okay, a computer does two things, and two things only. It performs calculations, and it remembers the results of those calculations. So yes, fundamentally, a computer only does two things. Now you might be thinking, well, no, a computer does all sorts of things, right? Plays videos, music, displays graphics, etc. Yes, that's true. But it all really comes down to, fundamentally, it all comes down to, so when they say calculations, they're not talking about like mathematical calculations. I mean, yeah, in one respect, it could be mathematical calculations. They're referring to logic. A computer goes through logical, critical thinking processes, similar to what the human brain does, but then at the same time, a computer also has a memory like the human brain does, right? That's the two key features of the human brain and of the computer. The ability to critical think, perform a critical analysis, but at the same time, you need that memory to supplement that, right? Without the memory, it all doesn't work. It all falls apart. You have to be able to store information and then forget about it in your present state of thinking, but then come back to that information if you need and access it. And so even to play a video or display some graphics or whatever, it's just a matter of going through a logical process about what needs to be done and then just outputting that. And then also at the same time, accessing the video or whatever need be in memory. Okay, however, but the computer does those two things extremely well. Yes, the big difference between the human brain and a computer is the computer can go through these logical thinking steps extremely fast. And then at the same time, it also can store significant more data in memory than a human can. And then furthermore, the computer is in general not going to make any mistakes like a human can. However, it just note that it is arguable that you could make the argument that no matter how advanced computers get, a computer could never surpass the analytical complexity capabilities of a human. So a human will always, no matter what, have a higher degree of logical, critical thinking ability than a computer because we build the computers. We create the computers, right? Yes, they could think faster, have bigger memory, but they could never out-critical think humans, out-analyze humans. That's an argument you could make. Okay, the typical computer that sits on a desk or in a briefcase performs 1 billion or so calculations a second. It's hard to imagine how truly fast that is. Think about holding a ball a meter above the floor and letting it go. By the time it reaches the floor, your computer could have executed over 1 billion instructions. As for memory, a small computer might have hundreds of gigabytes of storage. How big is that? If a byte, the number of bits in a byte is typically 8, required to represent one character, weighed 1 gram, which it doesn't, 100 gigabytes would weigh 10,000 metric tons. For comparison, that's roughly the combined weight of 15,000 African elephants. For most of human history, computation was limited by the speed of calculations of the human brain and the ability to record computational results with the human hand. So yeah, we do have, there is memory in the sense, for humans in the sense that we can record information and store it on paper. This meant that only the smallest problems could be attacked computationally. Even with the speed of modern computers, there are still problems that are beyond modern computational models, like understanding climate change, for example. But more and more problems are proving amenable to computational solution. It is our hope that by the time you finish this book, you will feel comfortable bringing computational thinking to bear on solving many of the problems you encounter during your studies, work, and even everyday life. Okay, so the big question then is the all-important question here that we're really wanting to get a sense of in this opening chapter in this video is what do we mean by computational thinking, right? It's saying for most of human history, computation was limited by the speed of calculation of the human brain and the ability to record information. But now with computers, we've enhanced our computational abilities. So what does this mean? What does computational mean? What does it mean to compute, right? A computer. That's what a computer is. It's performing computation. And so really what that means is the idea of computation is just saying, from the perspective of a machine, you're wanting to build a machine that's going to emulate what the human brain does, which is perform computations. And that doesn't mean mathematical computations. It's any kind of critical thinking combined with memory. If you have any kind of machine that can, again, emulate what the human brain does in terms of critical thinking and memory, that's what a computer is. And so one question we want to think about is, what's the bare minimum requirements, bare minimum fundamentals for some device or whatever to be able to have all of the functionality of the human brain, meaning it can perform any computation that the human brain can? What are the bare minimum fundamental requirements that you need to be able to do in order to truly think and compute like the human brain does? Okay, so we can start by thinking about, so what's interesting is that a computer, a modern computer, is truly a machine like any other machine, okay? Meaning that a computer is a device that has just mechanized the critical thinking and memorization processes. And so we want to start by thinking about, how is that possible? How could you possibly mechanize these processes? And so, okay, when we think about the word computer, if someone asked you, what's a computer? If your kids or your nieces and nephews asked you, well, what's a computer? We typically think about ones and zeros, right? Which is just referring to, in the mechanical sense, ons and offs for some portion of an electrical circuit. So the one is just a label we apply to a circuit that has a voltage or is on, and then zero corresponds to a circuit that has no voltage or is off, right? But one thing you want to think about is that a computer in and of itself is not married to ones and zeros, right? You might think, well, there's no computer without the ones and zeros, right? That's the inherent meaning of a computer, that digital ones and zeros, and that's incorrect. Yes, the modern computers that work based on the digital ones and zeros are so efficient and beyond the capabilities of any other type of computer that it's just overtaken the definition, right? But technically, a computer is any device that computes or performs some sort of computational thinking process to answer a question or solve a problem. You input something into the computer that requires critical thinking to figure out, and then the computer is going to output you the answer. And so you still might be thinking, well, but wait a minute, there's no way to make a computer without the ones and zeros, right? That's part of what makes it. That's the only way you can make a computer. Well, no. Okay, let's take a look at this example. So I'm going to put a link in the description to this video from the channel What Will Makes. It's a really good video. And in this video, he builds a purely mechanical calculator with no electrical components. Okay, but at the same time, you'll see that not only is there no electrical components, but this calculator isn't based on discrete digital on or off states. Or really not even on, off, just digital is more of, there's only the fundamental communication is just, it's a strict this or that, right? Well, that's not what this calculator is based on, like this just strict this or that. No. Okay, but this calculator is absolutely, in every respect, a computer. It computes. You input the number you want to start with, turn a crank, and it loads that number into the device. Then you set it to add or subtract, and you input the number you want to add or subtract, crank the wheel, and the output is the addition. That is a computer. It's critical thinking. Now, you might be thinking to yourself, well, no, that's not really a computer, right? Like we just talked about it's when it comes to having all of those fundamental features that can do what the human brain does, this doesn't have those features, right? And by and large, that's true. There are fundamental features missing from this calculator that a quote-unquote real computer could do. So what's missing? What exactly is missing? Well, scientists like Alan Turing in the early 1900s analyzed what are the absolute fundamental essentials needed to perform any kind of computation. And we're going to talk more about this in a few minutes. Okay, but so now these fundamental essentials are to perform any kind of computation, and the way I think about it is that the human brain can perform. I mean, perhaps the human brain is limited in terms of its computational abilities, and we just don't understand that, right? So what are the absolute fundamental essentials needed to perform any kind of computation that the human brain could possibly perform? Okay, so to do any computation or to solve any type of critical thinking problem, one of the essential features, absolutely critical, is you need the ability for conditional branching. So to be able to answer like if-then statements, if you receive this piece of information, now you have to make a decision, do this or that, or something else, etc. Right? Well, this doesn't have, if you watch this video, this doesn't have any conditional branching, okay? Now, also essential, also absolute essential, is the ability to have memory, stored memory, and then access that stored memory as you need, right? If we didn't have memories, we couldn't solve the problems that we solve in the world, right? Our memory is critical. Okay, well, this doesn't really have memory either, right? And then the final requirement, which is, this is really memory, but from a different perspective. The final essential is if you're going through a certain thought process that's currently active in your brain, so not stored in like a more of a longer term memory, you need the ability to be able to jump to like an earlier thought process that's not like in the linear sense, that the thought, you can't just be restricted to only think about just a previous thought you had right before. No, you have to be able to stop and say, like if you're working on a homework problem, you have to be able to stop and say, okay, wait a minute, I need to go to the start of the page and look at what happened and access some information, and then come back. Which again, that's kind of like memory, but from a different perspective. Those are the essentials. Okay, and so there you go, right? From this perspective, you look at this mechanical calculator and say that, well, they couldn't make a true computer, a true computation machine from just wood materials like this, right? And you would be wrong. Okay, as you watch this video, keep in mind that all of the mechanical concepts he's using to make the arithmetic work, he could use these same kinds of thought processes to construct a calculator that incorporates logic, memory, and jumps in current states of thinking. So like, try and imagine if, hypothetically, this was like a government-funded project. So Will, in the video, had many more resources, right? So like in the video, he's only using his tools and his expertise, but maybe he had any tools he wanted, any machinery he wanted. Perhaps he had help from professional machinists and woodworkers, and maybe he had 30 years to work on the project. The government was going to like pay him a salary. Well, then 100% he could make a full-blown mechanical device with no electrical components, just from wood and screws like he's doing here, that truly performs the fundamental tasks that a computer performs. The logic, the jumping to different states of current states of thought, the memory. And in fact, in this case, once he completed this project, in this case, he would have actually done more than is actually minimally necessary, because the portion that does the arithmetic is not an essential fundamental part of a computer. So if he made this more super wooden mechanical computer that's a continuation of this, in actuality, he would have made an arithmetic logic unit out of wood. which we'll talk about in more detail in a second, which again is above and beyond the minimal requirements. Now, yes, the amount of memory, the amount of logical operations that could be performed, etc., that would be incorporated into this device would be limited. Limited in terms of the scale, how much could be done. But still, the fabric of it, the ability to perform logic, to just automatically, with just cranking the wheel, perform logic, have memory, jump to different points in current state of thought, would all be there. And so this should all give you a much better sense for how it's absolutely possible to mechanize the computation process. And again, modern computers, though, do this via electrical circuits in the language of ons and offs, voltage present or not present. All right, so from the perspective of how modern computers operate, how could you use a network of ons and offs to perform all of the fundamental features of computation we just discussed? Okay, well, the first thing you want to note is that it's not an issue communicating whatever information needs to be communicated in terms of just ons and offs. So think about Morse code, for example. I could send an entire novel to someone using Morse code, which is just electrical pulses. Now, admittedly, Morse code actually isn't based on ons and offs. Off kind of isn't a primary part of Morse code. It's more of centered around these short and long pulses, which is still just two distinct signals. So you could argue it is digital, but also the off portion is kind of part of Morse code, so it's more of like a ternary, a three-part system. But still, the idea of being able to send Shakespeare to someone using just two separate electrical pulses should make it clear that communicating complex information with just ons and offs can be done. It's not a problem. Now, you might say, but wait, doesn't the input and the output with like Morse code have to be translated by humans? So like modern computers are fully independent. You know, I input the information in my native language on a keyboard, and it outputs the information to, you know, either back to me or whoever I send it to in just the correct language, etc. Don't worry so much about the translating or displaying processes. So the translating from the machine language of ons and offs to the human language of English, for example. And then at the same time, displaying this information via LEDs on a monitor. This is a secondary issue, okay? The hard part is not the translating from machine language to human language or the displaying of information. That's not the hard part. Okay, so all of the mechanical thinking processes of modern computers take place in the microchip or the computer chip. And really, the main reason there's such a disconnect between what we typically think of as machines, so something like a forklift or a vehicle or a bulldozer, and then something we think about as computers like our laptop, the reason why we put these devices into such different categories, and it's hard to think of a laptop as truly just as much of a machine as any other machine, is because of the microchip and how unique it is. For example, this image is of a microchip magnified 500 times. So if this was an inch on the page, then in the image itself, this distance would be an inch divided by 500. Okay, and so it's just mind-boggling how you could build something this detailed and intricate, this small. And then furthermore, just as mind-boggling is how could you control the electricity in all of these circuits the way you need it to? And so this is so different than the way we think about the operation of, say, like a forklift or our vehicle. All right, so how do electrical circuits think then? How do configurations of electrical circuits and the tracking of ons and offs within different regions of those circuits allow us to build a computation machine? Well, the building blocks of the entire microchip are what's called logic gates. Okay, and what facilitates the creation of these logic gates is transistors, which are just electrical switches, kind of like a relay, and that if you apply a current to the input, it will close or open the switch. Okay, and in the entire microchip, there's only 7 fundamental types of logic gates shown here. And any of these logic gates can be built with, on average, 2 to 6 transistors in the microchip. And so like the AND gate, for example, both inputs need to be high, have voltage, and only then will the output be high or have voltage. The NOR gate is the opposite of the OR gate. So the OR gate would be if either one of these are high, then the output will be high. Only if neither of these are high, then the output will be low, off. Well, the NOR gate is the opposite of this. So if both are off, then this will be high. In any other scenario, this is low. The output is low. And so what's interesting is that these 7 fundamental logical abilities are all that's needed to allow modern computers to perform any kind of computation or critical thinking analysis. And this kind of makes sense from the perspective that if you think about any thought process you've ever performed in your entire life, you really potentially could break it down to just fundamentally a large series of one of these types of logical questions being answered, right? And so the entire microchip is just made up of regions of configurations of logic gates. That's it. Hundreds of millions, billions of logic gates. And logic gates are grouped together into certain configurations so that as a unit they can perform more complex computations. So for example, one part of the microchip of your laptop is what's called the ALU, or the arithmetic and logic unit, which I had mentioned that for the enhanced version of this mechanical calculator, what you would in effect have is a very simple, much less powerful, but technically an arithmetic and logic unit. If this could perform some logical analysis, as well as jump to different points in the current state of thought and even memory as well. But technically in a computer, the ALU is more part of the processor, where like there's memory microchips. They're microchips just dedicated to memory, and then you have another microchip just dedicated to processing. But we're just right now just thinking about this more in general. Okay, but the ALU is the heart of where all mathematical calculations are conducted. Okay, and it's created using networks and configurations of logic gates. In the ALU, you're going to have like an arithmetic portion and then a logic portion. So the arithmetic portion is what's doing the math. It's still made up of just configurations of logic gates, but then there is like a logic portion that's more dedicated to deciding what to do with completed calculations. But it's all just logic, all logic gates. But what you might find interesting is that even in the most powerful computers, the ALU, as the name implies, only performs arithmetic. So addition, subtraction, multiplication, division. But as we know, modern computers can solve differential equations, solve some of the most complicated matrix algebra, linear algebra problems used in, for example, finite element analysis simulations. But still at the same time, in the main central process unit, the core heart of the computer, the microchip portion that's dedicated to mathematical computations, it's only doing arithmetic? How is that possible? How does that make any sense? Well, this leads to another central idea of how exactly computers operate. And really, this also might give us insight into how the human brain operates as well. So all of the regions of the microchip outside of just the ALU have a similar sort of basic functionality in regards to what they're associated with, in the same way that the ALU has a basic functional capability in regards to mathematical calculations. And so once you do a little bit of your own reading and watching videos, it's simple to understand how you could build an electrical circuit composed of logic gates. And with this circuit, you could take any number like 7,423, translate this number to binary, input this binary number as high and low voltages into the circuit, give the circuit some sort of operation command like multiply in the form of an electrical signal, input another number like 218 into the circuit, run the circuit, and an output will be given in the form of highs and lows, and you would translate this number from binary to decimal to get, it would be what, 1,618,214. It's really not that complicated to understand how you could build an electrical circuit, a network of logic gates that could do this. And again, don't get bogged down with the display process in that actual computers display values on screens with LEDs. This is a secondary issue, okay? And it's also in the same way, it's simple to understand how memory can be constructed with just configurations of logic gates. So all of the fundamental critical thinking features of being able to perform computations in the same way a human brain does can be constructed with configurations of logic gates. Okay, but again, even with hundreds of millions, billions of transistors and logic gates, from a pure mechanical perspective, the microchip is only performing critical thinking and analysis to so much complexity, right? Like the arithmetic and logic unit. So how then are computers able to perform logical analysis way past just like the simple arithmetic or a simple kind of critical thinking process? Well, this is done with algorithms and programs. So let's keep reading. Okay, all knowledge can be thought of as either declarative or imperative. Declarative knowledge is composed of statements of fact. For example, the square root of x is a number y such that y times y equals x. This is a statement of fact. Unfortunately, it doesn't tell us anything about how to find a square root. Okay, imperative knowledge is how-to knowledge or recipes for deducing information. Okay, so it's interesting they're saying that all knowledge can be put into one of two categories, either declarative or imperative. With declarative, you're just stating a fact or like a definition, right? But imperative is more of like a how-to in terms of how to obtain some information, deduce some information, obtain some knowledge, how to bring a statement of fact, let's say, into reality. Okay, the term imperative means giving an authoritative command, and it's a almost like a law. Here's the steps to the how-tos for deducing this information. Follow these steps precisely, exactly in this order, and you can obtain or deduce this information. You could deduce the information contained in a declarative statement, for example. Like the declarative statement here is telling you what the square root is. The square root of a number is. But okay, if you're given a number, then how do you determine the square root of that number? Right? That would be the imperative knowledge corresponding to this declarative knowledge. So Heron of Alexandria was the first to document a way to compute the square root of a number. His method for finding the square root of a number, call it x, can be summarized as, okay, so you're given a number x, and you want to find what the square root of x is. So you start with a guess, g. Then you multiply g by itself and compare g times g to the input. You could compare it using like a percent difference, for example, which would just be you subtract g from x and divide by g or x. And then how the magnitude of the percent difference, if it's small enough, then you stop and say g is the answer. If it's too big, that percent difference is too big, then you can create a new guess with some sort of like averaging step, averaging the first guess with, say, something like x divided by g, and then to get a new guess, and then you just go through the same process with that new guess until the new guess times itself is close enough to x. And then that final guess is you report that as the answer for the square root of x. So, for example, considering calculate the square root of 25. So we set g to some arbitrary value like 3. Then you say, okay, multiply 3 by itself, you get 9. Compare 9 to 25. The percent difference is too big. So you make a new guess, which would be 3 plus 25 divided by 3 divided by 2. The average of 3 and 25 divided by 3, 5.67. Now, this is the new guess. Multiply this by itself. 32.15. That's still too far from 25. So now same process. Average 5.67 with 25 divided by 5.67, and you get a new guess, 5.04. Multiply this by itself, 25.4. Whatever your depending on what you specify to be the accuracy requirements. In this case, they're saying, okay, that's close enough to 25. So you're saying the square root of 25 is 5.04. Okay, so let's think about what we did here, what we just did here, right? Because we're so ingrained in 21st century culture. If someone asks us to calculate the square root of a number, we just use a calculator, right? And there's nothing wrong with using a calculator, because if someone asked us, what's the square root of 17? Okay, so we go to a calculator, get this value, but we know exactly what this value means. We understand the declarative knowledge completely. We know that if you take this number and go to a piece of paper and multiply it by itself, it's going to be either exactly 17 or very, very close to 17. Okay, however, if all of a sudden we didn't have a calculators to work with, and someone asked us, what's the square root of 17, we would be stumped at first, right? But then if we really wanted to get the answer, it wouldn't be a problem, because we know how to multiply decimal numbers on paper. We could just go through a guess and check process like they did here until we found a number that, when multiplied by itself, is close enough to 17. Okay, but this process that we just went through, you can think about, like, in general, a process like this that you go through to get the answer to something. What are the constraints here? Well, first, there's an assumption that whatever you're giving these instructions, like whatever or whoever is performing these instructions, you're assuming that this thing or person is able to do exactly what you're telling it to do. So a part of instructions like this is, what exactly is the system able to completely do on its own? And so in the case of a computer, what we're referring to is, so like mechanically, from a mechanical perspective, what can the machine, the computer, do on its own? Now, I do want to point out that, so you might be thinking that when it comes to math, what's the minimum amount of information a system needs to know on its own to be able to solve like any math problem, right? So it's got to be able to do arithmetic on its own, at least, or else you can't do any complicated mathematical computations. It has to be able to do arithmetic, the fundamental operations of math, right? Well, no, technically, no. Technically, the system, the mechanical system, doesn't need to know anything about math from the start, right? The ALU, as we talked about, is built from logic gates. So technically, you could solve any math problem where from the start, you start the instructions by pretty much teaching the system math, or like you just start from the absolute basics of where like the ALU starts, where it doesn't know anything about math to start with, right? Math in and of itself is logical. The idea of adding, subtracting, multiplying, dividing is just a logical process. Okay, but it's obviously not practical to do it that way. If you want to, every time you want to do any kind of math operation, you have to like work completely from scratch. So to a certain extent, you're going to need to mechanically build in some inherent knowledge into the microchip, right? Like in the case of math, you're going to have to you're going to need to inherently build in the fundamental math operations: add, subtract, multiply, divide. So you can just make a statement like, okay, load this number. Now take this number and add it to that number, multiply that number. You don't have to, every time you want to add something, break down the full logical steps of what adding means. Okay, but now also, though, what you want to think about is it's going to be the case that at some point you won't be able to mechanically build in logic. You might say, oh, why don't you just build the entire arithmetic and logic unit mechanically to where it could solve a differential equation purely mechanically, right? But like that, at some point that's not feasible. Like maybe you could mechanically build in a square root calculator, but if you keep going, that at some point there's not going to be enough space, like physical space in the microchip, to calculate or reason through something purely mechanically. Okay, but mechanically in the microchip, being able to do arithmetic is a great starting point, because like addition, subtraction, multiplication, and division, again, they are the fundamental operators in all of math. Like you might say, well, no, there's roots, exponentials, logarithms, powers. Well, no, all of that is just packaged forms of multiplication and division, right? Think about the definition of an exponential, a logarithm, powers. It's just multiplication or division mixed in there. That's the fundamentals. In the same way that fundamentally multiplication and division are just packaged forms of addition and subtraction. Even like the derivative, right? The derivative, it's a quotient. Again, you have the logical thought process of the limit portion of the derivative, but outside of that, it's a quotient. It's a slope. You subtract two values and then take that subtracted value and divide it by another value. Okay, and so what you can see here is that we can take advantage of the fact that we can write out steps like this, and the computer is going to be able to cycle through these steps extremely fast. Okay, but at the same time, though, built into the functionality of the mechanical functionality of the microchip, what we're able to do is with these kinds of instructions is we can incorporate logical statements like if-then statements, loops. While this is this, do that. You could store information, right? Set this, okay, remember this value, and now while this value is this, then cycle through these steps, these loops. You can jump to different portions of the steps as you need. All that functionality is mechanically built into the microchip, right? We have all the abilities necessary with these instructions to think like a human brain thinks. The memory, the jumping, the conditional statements. Okay, but however, the big difference, though, again, is that the computer can go through these steps insanely fast and at the same time with an insane amount of memory. Okay, and a list of steps or instructions like this that need to be progressed through to perform a computation or some sort of analysis is called an algorithm. Okay, so note that the description of the method is a sequence of simple steps together with a flow of control that specifies when each step is to be executed. Such a description is called an algorithm. All right, so it's important we understand the difference between an algorithm and a program, because these are two distinct concepts. They're related, but they're distinct. Okay, they're related in the sense that both are step-by-step procedures to solve a specific problem. That's one way you could describe both an algorithm and a program. However, an algorithm is more of an abstract concept, whereas a program is a concrete implementation of the algorithm. So you can think about it this way. You start with some declarative knowledge, like the definition of the square root, but to really help in understanding the difference between an algorithm and a program, let's think about a much more difficult declarative statement. like maybe something related to climate change, right? You could make a factual statement about, look, this is what the climate is doing, and how could we take certain data and make a prediction, etc. Okay, well, an algorithm is just a abstract description of, okay, how could I program a computer? What steps would I use to allow a computer to make these calculations? Would I use some guess and check algorithms? What could I do? You could write an algorithm on notebook paper in whatever language you want, however you want to describe it. Like, okay, I'm going to mix in this many guess and check procedures. We're going to pull these values and then run through these loops. And when you do all that together, then this is going to give us the result we need. You analyze algorithms. An algorithm is something you analyze. And an algorithm, again, can be written in any language. It can be described in any way you want. An algorithm fundamentally has nothing to do with like a certain hardware or operating system, nothing like that. It's an abstract concept. A program, on the other hand, is the implementation of an algorithm. So once you've got your strategy for how you're going to direct the computer to determine some climate change information based on some input data, the algorithm, then you would give this algorithm to a program writer. And their job is to, okay, I need to write the code that's going to implement this algorithm. We can't just scan this notebook paper and put it into the computer and it's going to run the algorithm, right? So you see the difference? Like this is a program. This is something the hardware can actually implement. Whereas an algorithm is just like the abstract description of the program. So yes, a program and an algorithm are absolutely related, but they're still two distinct concepts. Okay, so this square root algorithm is an example of a guess and check algorithm. It's based on the fact that it's easy to check whether or not a guess is a good one. Yeah, so I think without any programming experience, probably we're all inherently familiar with a guess and check algorithm. If somebody asked you, if you knew how to do any kind of arithmetic on paper really well, and you knew what the square root meant, you know what a square root means, and if there's no calculator, somebody asks you, okay, what's the square root of 67? And you're like, and you're kind of taken back at first, and you're like, well, no, I could figure this out. And you're going to naturally, I think we would all naturally use a guess and check algorithm. You just need to find some number that when you square it is as close or maybe exactly equal to 67. Okay, well, 8 times 8 is 64, so let's start with 8.1, and you just go from there. If you overshoot 67 too much, then you make your next guess a little bit lower, right? Well, that's what, when you study numerical methods with, like for engineers, scientists, etc., with programming, or even just studying programming in general, what you can think about is there, with all of the professional programmers and research in programming, there's a lot of very clever ways to write programs to solve problems outside of just guess and check algorithms, right? You know, it's not always just, okay, you're going to have to just make every time it's all about just guessing and trial and error. No, I mean, there's a lot of brilliant ways and techniques that are used in programming to answer questions and solve problems, all right? A bit more formally, an algorithm is a finite list of instructions that describe a computation that, when executed on a set of inputs, will proceed through a set of well-defined states and eventually produce an output. Yes, so an algorithm is it's a computation. It's not just a math computation. It's a critical thinking process to answer some question. And what you're doing is you're just proceeding through these sets of inputs. And the way you want to look at this is, so the computer is, like, it does have memory that it can use, but it's really, in general, the way you want to think about it is it's going through these steps and it's just forgetting what it did previously unless you tell it to remember something, right? It's got this number it starts off with in the register, and then you'll start, it'll do a step, do a calculation, and update that number to something else. Then go through another step and update that number to something else. It doesn't, and usually the previous number is just lost unless it's told to store it, right? It's just going through Send electrical pulses through the microchip and get a new value. Send electrical pulses through the microchip, get a new value. If you want to store something, you can send electrical pulses into the memory and store something. It's going line by line by line, and also it could skip lines or go back to previous lines, just line by line by line by line, new calculation, new calculation, new calculation, to where you started with an initial value in the register and you ended with a final value in the register. And the computer has no idea where it came from. Only you really understand that. But then also at the same time, in most cases, you have this initial value in the register, this final value in the register, and then a bunch of stored stuff in memory. But it's helpful to kind of think about how the computer, when it's all done, if you think about the computer kind of like a person, it has no idea what it just did. It just went line by line by line, sending pulses through the microchip, updating the register, pulses through the microchip, updating the register, pulses through the memory. Now there's some things in the registers of the memory. Okay, now there's also some tests for deciding when the process is complete, as well as instructions about the order in which to execute instructions, sometimes jumping to a specific instruction based on a test. So yeah, another important feature of the computer is going to be the counters and the timers. What's going to tell the computer to go to the next step? And also, at the same time, what's going to tell the computer to stop? Okay, and so now the original computers, you can imagine the first computers were what's called fixed program computers. So the wooden calculator would be a fixed program computer because they're, like it says here, they're designed to do very specific things. It's a computer that just does one program. Here it's adding, subtracting, and then multiplying, dividing. That's it. The old handheld calculators, not the new scientific calculators, the handheld calculators, they're really specific. They're designed to do one type of task. So there's what that means is it's like there's just one main algorithm in that computer, one program. There's the recent movie that came out 5 or so years ago about the Enigma codes, the breaking of the German Enigma codes. That was like one of the original computers. That was a fixed program computer. It was designed to do one task. Okay, but modern computers, what we really think about as computers today, your laptop, these are stored program computers. Such a computer stores and manipulates a sequence of instructions and has components that will execute any instruction in that sequence. By creating an instruction set architecture and detailing the computation as a sequence of instructions, like a program, we get a highly flexible machine. By treating those instructions in the same way as data, a stored program machine can easily change the program and can do so under program control. So what they're talking about here is, so like I could write a square root program. A program that you could calculate the square root with the ALU and the microchip, right? Then I could store that program on the computer. And so when I want to calculate the square root of a number, I don't have to write that, just keep writing that code from scratch, right? So here's MATLAB, for example, right? So if I want to get the square root of 64, I just use this function, or the square root of 17. Right, but it's not that the square root function is built in mechanically into the microchip. No, it's the stored program computer feature. The square root program, based on an algorithm like this, is stored into the computer. So it's just going to memory and pulling that program and running it. And on like a bigger scale, that's what, when you run Microsoft Word, Microsoft Excel, etc., the programs that run those computers, the algorithms, they're stored in memory, and then when you click on something, it calls on that program and it runs it. Okay, now, but how do computers run? Like, don't we run programs at the same time? You could have you're playing a game and you're surfing the internet at the same time, right? Well, how does that work? Well, assuming there's not multiple microchips, multiple processors, the idea there is, I don't want to go into too much detail in this introduction, but you're technically never actually running programs at the same time. They're just like, it could be, for example, it's kind of like the way you multitask. Your brain multitasks. Do you when you're multitasking, do you ever literally do two tasks at the same time? No, right? You're just splitting it up. You're doing at one time you're doing this, then you switch and you just keep switching back and forth. Well, the computer is just switching within like milliseconds, microseconds. It's just going back and forth. It's doing it at the same time, but not literally at the same time. But again, that's more advanced topics. I'm just trying to give you an introduction here. Okay, so indeed, the heart of the computer then becomes a program called an interpreter that can execute any legal set of instructions, and this can be used to compute anything that one can describe using some basic set of instructions. So yeah, the interpreter, and also the same idea is the compiler. They do the interpreter and the compiler perform the same overall function, just in different ways. But Python uses it in an interpreter, but other programming languages like C and C++ are compiled programming languages. Okay, the programming code, which is this is still relatively easy for humans to understand, right? You're writing things like we just did, square root, or you're using the add symbol, the subtract symbol, the word print, right? It's still we can read this, but computers only speak in ones and zeros, right? So the interpreter or the compiler is converting the program into a language that the computer can understand, and then it can run that program. It can just, again, it's just going line by line. Just like we did this algorithm line by line, that's what the computer is going to do. Now, it's line by line, but it could also, remember, you can still jump. You can go through loops, but it's still, in general, like a line by line thing. Okay, and so it just to give you an overview here, for just like a typical computer like your laptop or desktop, it's like I had mentioned, you're really going to have a separate dedicated microchip for processing, and then a separate dedicated microchip or microchips for memory. You're not going to have the memory. You can have the memory kind of on its own and the processing on its own. And so the idea is like you've got all this stored data here, and then when you call on to run a program, the interpreter or the compiler, and I'm going to really give you a big overview here because the interpreter is a bit different than the compiler. Really, more of the compiler you can think about is going to translate all of your program code, which is called source code, like the Python code, for example. Well, let me not say Python. Let me say C or C++, because that's a compiled programming language. That's going to be translated into machine code. These lines of binary. And in the memory, it's going to, the computer's going to execute that binary machine code. So it's like you're going to have stored programs in the data, like the square root calculator program, for example. When you call on it, it's going to be put into the portion of the memory unit that is going to execute the instructions, execute the algorithm or the program. It's going to, in conjunction with the processor, it's going to execute those instructions using machine code, right? So using machine code, these lines of ones and zeros, you're going line by line. The computer can take a binary string and interpret that as, okay, what electrical signals do I send through the microchip? And then it's going to update the register, right? You're going to go line by line. Or then again, or you might do a loop, or you might jump to another line. Once the operation is done, you're going to have like a final value in the register of the processor, and then in general, a bunch of stored data that you can then output to the user. Okay, now again, we're going to get into more specifics later in the course, but the compiler is really just taking the entire program and converting it to machine code, these lines of ones and zeros, lines of binary strings. But the interpreter is a little bit different. It's not exactly like that, but they're both, the interpreter and the compiler are performing the same functions, though. It's just executing your program in binary with the processor. But we'll get into more specifics on how interpreters and compilers work later. Okay, so both the program and the data it manipulates reside in memory. Yeah. Typically, there is a program counter that points to a particular location in memory, and computation starts by executing the instruction at that point. Most often, the interpreter simply goes to the next instruction in the sequence, but not always. In some cases, it performs a test, and on the basis of that test, execution may jump to some other point in the sequence of instructions. This is called flow of control and is essential to allowing us to write programs that perform complex tasks. So yes, it's essential that you're not just, the computer is not just constrained to follow line, and it can't go backwards. It can't jump to some other spot. That's essential to do any kind of computation. Flow of control is essential. And we can do that, right? We're allowed to write algorithms where we can do loops, for loops, while loops, or we can say jump back to step, this other like step. And you might be wondering, well, how does the computer make flow of control work? Didn't I just talk about how the CPU is sort of going line by line, updating the register, and in essence, sort of forgetting about what it just did unless it's specifically told to remember something? Yes, that's still true. But the general idea when running a program is the CPU is going to have the entire program with all of the steps in memory. So maybe it doesn't remember the computed value associated with some previous step, again, unless told otherwise, but it can still jump to any step it's told. Okay, so to create these sequences of instructions, we need a programming language in which to describe them, a way to give the computer its marching orders. Yeah, so there's just different programming languages that are used to, like it says, give the computer its marching orders. Tell the processor in conjunction with the memory what to do. There's different languages that you can use that you'll write the program in this, the source code in this a certain language, and it gets converted to a binary machine code. Given any general algorithm, this algorithm, there's different programming languages you can write that algorithm in. Okay, now the universal Turing machine, the Church Turing thesis, the halting problem, Turing completeness. These are all really interesting concepts that are related to the fundamentals of the idea that we talked about earlier in terms of what is fundamentally required, the bare essentials for a machine or some system to be able to fully think and reason and compute like the human brain can compute. What are the absolute fundamental essentials? And so what's interesting about this, the universal Turing machine, is the way you can think about this machine. So I'm going to post another link in the description to another video where a guy builds one of these universal Turing machines, but it's technically not possible to build an actual universal Turing machine. So, and I'll tell you why in a second. And so the idea is, what is the simplest machine you could build with as basic a functionality as possible, that even though it might take a while, even though it might not be the most efficient, it has the ability to compute anything that, like any of the most high-powered computers that we work with today could compute. Okay, and the best example of this is the universal Turing machine. So all this is you've got these rolls of tape on both sides here. So this tape can go forward or backward. And the reason why it's technically not possible to build an actual universal Turing machine is because a true universal Turing machine would have an infinite amount of tape on both sides. Okay, and what this machine does is it's got this marker here. So these are like the way this guy built it. These are like these dry erase board type tape pieces here, and with a dry erase marker, you've got a camera here that can just read whether or not there's a 1 or a 0 written on the tape. Okay, and then there's a dry erase marker here that when you command it to, it can erase numbers. In at the head of the marker, you can upload a program, but the program is going to be based on, you can tell the system to, okay, you're going to read a number, and after reading that number, you tell the marker to, or the system to, you could say, okay, maybe don't change the number and go to the next number in line, either forward or backward, or jump to some other portion of the tape. Or you could tell the dry eraser to erase a certain number, and you're going to change it from 1 to 0 maybe, or 0 to 1. Okay, that's it. That's the only functionality of the machine. And the idea is, okay, so we talked about how with just ones and zeros, you could, in this band of tape here, you could write a Shakespeare poem, write a Shakespeare play. assuming you've got it's like an infinite amount of tape, this hypothetical infinite amount of tape, right? So the idea is you would encode in ones and zeros what you want solved. Then you would put it into the universal Turing machine. It would go through and scan everything to read your problem. Then it would go through the program with just the erasing, writing a new number, jumping here and there. And when it's done, you'd have this new band of tape with this new band of ones and zeros. And when you translated that, that would be the solution to the problem. And the idea is this is technically, with just this machine, you can compute anything that a modern computer could compute. Like, this has the brain power to do it. Like, you might say, well, what about the memory? Well, no, it's an infinite amount of tape. So like at the back or front end of the tape would be all of your memory. You could just store whatever data you need in memory. Now, this is obviously hypothetical. If like for a challenging problem, this would take forever for the machine to do, and then also for you to encode the problem in binary into the tape initially, and then come up with the algorithm for moving the head to solve the problem. But it's just a hypothetical thought exercise. Okay, and so the Church-Turing thesis states that if a function is computable, a Turing machine can be programmed to compute it. And that's the idea of Turing completeness. A programming language, along with the computer it's operating with, is said to be Turing complete if it can be used to simulate a universal Turing machine. It's just saying that it has the ability to compute anything you want it to compute. Now, it's still nothing is technically Turing complete because you don't have an infinite amount of tape, an infinite amount of memory, right? But it's just like, again, it's like a hypothetical thought process. Okay, now just note that all of the main programming languages are Turing complete, like the C, C++, Java, Python, MATLAB. It's all Turing complete. Again, this is all really just to help with our conceptual understanding of computers and how they work. Now, the halting problem, what the halting problem is talking about is, so this is answering a question about, it's a theoretical question of whether it's possible to create like an algorithm. So you want to write an algorithm that, using this algorithm, you could input a separate program into the algorithm, and that algorithm will tell you whether or not that program has a solution. So when you run that program, is it going to halt or is it going to run forever because there's no solution? Is it possible to create a program and an algorithm that could do this kind of analysis? And Turing determined that the answer to this is no. And he was able to show this with like a proof by contradiction technique. Like, it was like if you hypothetically had an algorithm that could do this, then he reasoned that you could then put this algorithm into like an overall bigger algorithm with its own inputs, but then the inputs into this bigger kind of black box algorithm would result in a contradiction. Okay, so all modern programming languages are Turing complete. As a consequence, anything that can be programmed in one programming language, like Python, can be programmed in any other programming language, like Java. Okay, so yeah, that's another way of looking at Turing completeness. So like on your computer, your laptop, you could run MATLAB or Java or Python. Okay, well, all of these programs are interacting with the microchip, right? They're all interacting with the memory and the processor, and they're all Turing complete. So it's like you might think, oh, well, I could build a website with Java. I couldn't do that with MATLAB. No, technically that's not true. Now, but like it says, though, it says, of course, some things may be easier to program in a particular language. Some programming languages are designed, they're catered to specific tasks, like MATLAB being catered to more mathematical calculations. But all languages are fundamentally equal with respect to computational power. You have the same abilities to manipulate the processing microchip of the computer in any way with MATLAB, Java, Python, or any other programming language that's on your computer that's Turing complete. Okay. Fortunately, no programmer has to build programs out of Turing's primitive instructions. Instead, modern programming languages offer a larger, more convenient set of primitives. However, the fundamental idea of programming as the process of assembling a sequence of operations remains central. So yeah, it's not like all programming languages have to operate with just the basic types of instructions in a Turing machine. No, they optimize it, right? That's like the whole idea of the arithmetic and logic unit. You could teach for every time you wanted to do a calculation, just like reteach the processor math, but no, they build in this ALU to make things more convenient, more efficient. Same idea with programming languages. Okay, there are hundreds of programming languages in the world. There is no best language, though one could nominate some candidates for worst. Different languages are better or worse for different kinds of applications. MATLAB, for example, is a good language for manipulating vectors and matrices. C is a good language for writing programs that control data networks. PHP is a good language for building websites. And Python is a good general-purpose language. Each programming language has a set of primitive constructs, a syntax, a static semantics, and a semantics. By analogy with a natural language, like English, the primitive constructs are words. The syntax describes which strings of words constitute well-formed sentences. The static semantics defines which sentences are meaningful, and the semantics defines the meaning of those sentences. Okay, so a primitive in a programming language is going to be a built-in data type. So it's like built into the processor. That's as fundamental as it gets. It has one meaning. Okay, like an operator such as add, subtract, multiply, divide, or a number or a string of letters. Okay, like with a literal being a single value that's written directly into the code, like this single number, this single string, this single like Boolean, true or false. Whereas it's like these infix operators. So like an operator it's not a value. This is still a primitive. A literal is a primitive and an operator is a primitive, but this is not a value. It's an operator, right? Add, subtract, multiply, divide. And what they're talking about infix, this is like in relation to the syntax. So you're going to do, in the code, you'll do 3 times 2. It's infixed, as opposed to like that you could have a prefixed language where you would do like this. This is 3 times 2. Or there's postfix where you'll put the operator at the end. Okay, and so that's related to the syntax. The syntax of a language defines which strings of characters and symbols are well formed. So like with the sentence example, you've got the primitives are the words, but you can't just arbitrarily string words together and have a well-formed sentence, right? You can't say cat, dog, boy. There's 3 nouns here. And in the same way, you couldn't do this for an infix with use of infix operators. These two would not be syntactically valid. So in Python, the sequence of primitives 3.2 plus 3.2 is syntactically well formed, but the sequence 3.2 with no, like a quote unquote verb in the middle is not. Now, but we have to go further than this because, so next is the static semantics. We could have a primitive here, an operator, and a primitive here, so that's syntactically correct. But what if one of the primitives here was a Boolean or a string plus a number? Well, that doesn't make sense, right? It's the same way that in a sentence you could have they got like a pronoun, verb, adverb. That's grammatically correct, but the sentence still doesn't make sense, right? And that's the static semantics. So there's dynamic semantics, but the static semantics, they're called static because you can think about how they could be checked before the program is run. Checked and then fixed, right? You could find this. You could say, well, look, no, you can't have a number and then divide with this operator and then a character, okay? But the dynamic semantics of a language associates a meaning with each syntactically correct string of symbols, but there's no static semantic errors. So you could still, even if the syntax is correct, the static semantics are correct, you could still have issues. And that's what dynamic semantics are about. It's more about the meaning of the program once it executes. It's like it's hard to find these dynamic semantics without executing the program to some degree. Like the idea is a sentence, I cannot praise this student too highly. Well, like it's saying, that could be flattering or damning, right? And you could have the same kind of ambiguity when it comes to a line of code. So programming languages are designed so that each legal program has exactly one meaning. Those syntax errors are the most common kind of error, especially for those learning a new programming language. They are the least dangerous kind of error. Every serious programming language does a complete job of detecting syntactic errors and will not allow users to execute a program with even one syntactic error. Yeah, absolutely. Furthermore, in most cases, the language gives a sufficiently clear indication of the location of the error that it is obvious what needs to be done to fix it. Yeah, so when you're writing a code, if there's an error in the code, it'll usually in real time, sort of like in Microsoft Word, where it'll underline a word that's like misspelled. It's the same idea with programming. The situation with respect to static semantic errors is a bit more complex. Some programming languages, like Java, do a lot of static semantic checking before allowing a program to be executed. Others, like C and Python, do relatively less static semantic checking before a program is executed. Python does do a considerable amount of semantic checking while running a program. Okay, now for semantic errors, dynamic semantic errors, one doesn't usually speak of a program as having a dynamic semantic error. If a program has no syntactic errors and no static semantic errors, it has a meaning. It has semantics. Of course, that isn't to say that it has the semantics that its creator intended it to have. When a program means something other than what its creator thinks it means, bad things happen. So yeah, just to make it clear, you might be scratching your head a little bit thinking, so like, how are dynamic semantics even possible? I mean, isn't a computer, it's like a rigid machine, right? There's no ambiguity in the microchip. We're talking about the programming language. What they're referring to here is built into the underlying program of the programming language. It's like there could be autocorrect features. So you can, with Python, you could enter in, say, x is equal to 1, and now x is defined, the data type is a floating point number. But then if you then said that x is equal to, the word hello, it'll change this data type to a string type. Whereas like other programming languages, you can't do this. Once you have to define, look, this is an integer or a floating point number, and now x is this variable, you can only put integers into that box, right? And so it's the background program of the programming language in the sense of like kind of like the autocorrect features, the little nooks and crannies that allow you to write the code. That's where dynamic semantics come in. Really, dynamic semantics issues are more associated with you not having a complete mastery of a certain programming language and how it works. When you go to run the program, it's not operating like you thought, and you don't understand why. And the reason is because it's not that the machine code is telling the microchip to do exactly what you were wanting it to do. If that was the case, then it would work. It's more of like, okay, well, what machine code did it translated the program I put into some machine code, and there's a disconnect there because of the dynamic semantics involved. There's nothing wrong with the program. The program is executable. There's no syntax errors. There's no static semantics errors, right? The program has a meaning. It's fine, but it's not doing what you intended it to do. Okay, when a program means something other than what its creator thinks it means, bad things happen. What might happen if the program has an error and behaves in an unintended way? It might crash. It's like stop running and produce some sort of obvious indication that it has done so. In a properly designed computing system, when a program crashes, it does not do damage to the overall system. Of course, some very popular computer systems don't have this nice property. Almost everyone who uses a personal computer has run a program that has managed to make it necessary to restart the whole computer. Or it might keep running and running and running and never stop. If one has no idea of approximately how long the program is supposed to take to do its job, this situation can be hard to recognize. Or it might run to completion and produce an answer that might or might not be correct. Each of these is bad, but the last of them is certainly the worst. Yeah, because you're getting a false answer, right? That's how accidents in real life happen. When a program appears to be doing the right thing but isn't, bad things can follow. Fortunes can be lost. Patients can receive fatal doses of radiation therapy. Airplanes can crash. Whenever possible, programs should be written in such a way that when they don't work properly, it is self-evident. We will discuss how to do this throughout the book.